All right. So, okay, let me start. Today I'm going to talk about my recent work with Vladimir Belavin on torus one-point correlation numbers in minimal level gravity. I will try to explain shortly what's that about. Well, the talk would probably be rather technical because the paper is very technical as well. But first, let me start a little bit with some background and motivation for why are we calculating what we calculate. So we will be considering a certain model and formulation of two-dimensional quantum gravity, which is called Liouville gravity. It is based on the functional integral approach to quantum field theory. Basically, if we consider quantum field theory of some CFT coupled to two-dimensional metric, which is dynamical, it is convenient to fix the conformal gauge in the integral over metrics. And according to the conjecture of David Dislin-Kawai, we get, after the usual gauge fixing procedure, introducing BRST ghosts and all that, we can equivalently rewrite this theory as a CFT of total central charge 0, where the dynamics of gravity is replaced by a Liouville CFT, where the Liouville field is just a conformal factor of the metric. And well, these three sectors that I described here, gauge fixing ghosts, matter CFT, and Liouville CFT, become formally decoupled. So the only, at least in the level of the action. So the only remains of the fact that matter CFT was coupled to gravity is the requirement on the central charge. So a particular case is of interest is when the matter theory is a CFT minimal model, which is commonly referred to as minimal level gravity. And it was long ago suggested that it has an equivalent, or at least somehow related formulation in terms of the double scaling limit of a matrix model, which is another well-known approach to two-dimensional quantum gravity, inspired by the idea of discretization of random surfaces. So yeah, we take the double scaling limit of matrix model, one matrix model, two matrix model, depending on what minimal model we consider, in the vicinity of a multi-critical point, and we get something equivalent to this continuous formulation, minimal level gravity. This is the proposition. But well, there are two problems with establishing if it's true or not. The first one is that we would like to identify the generating functionals of the two theories, one in matrix model and one in Liouville gravity. But the precise relation between coupling constants in two cases is a bit obscure. They are not precisely, well, at least the ones that are natural to define in both approaches are different and apparently related by a certain analytical definition, which are called resonance transformations. Also, the observables that are natural from the matrix model side, which are a derivative for the generating functions, on Liouville gravity side are given by integrals over certain modular spaces, which are difficult to calculate analytically. So the checks of this relation were performed only before our work. Were performed only up to 4-point correlators on a sphere in genus 0. This was done a long time ago by belonging to Molodchikov. I mean, the calculation of the 4-point correlation numbers. It was possible due to the discovery of so-called higher equations of motion in Liouville conformal field theory. And basically what we did in our paper is to adapt the method based on higher equations of motion to the case of higher topology. Before our work, the work on Liouville gravity on surfaces with genus greater than 0 was mostly limited to numerical checks and some very specific cases, which I'll probably mention in passing in what follows. So yes, I'm going to describe the method which allows to compute the 1-point correlation function of certain observable, called otherwise the tachyon vertex operator, for the case of torus topology genus 1. In what follows, I will further limit myself to the series 2 to p plus 1 of minimal model, the Lie-Yang series, which is more of a technical simplification. I think that it is relatively painless to adapt it to a more general case, but this is the case when the expected answers from the matrix model approach are most understood, as well as resonance transformations. So to have something to compare our results to, we will limit ourselves to the Lie-Yang series. I will start with demanding some technical facts, some prerequisites, which will be important in our derivation. First, let me discuss some general properties of correlation functions on the torus valid for any conformal field theory. I will denote by tau the modular parameter, usual model parameter of the torus, and q is the form function, the exponent of 2 pi I tau. So we will frequently use, most of all, conformal word identities, which express how the correlators of primary fields with insertion of stress energy tensor in CFT relate to correlators without insertions of T. In the following, you can see how they look for the single and double stress tensor insertion. Probably we won't need the last one. I'm not sure if I'll go into the details about the case. We will need this, but so that's basically how they look. The correlation function with insertion of T can be obtained by this one reaction of certain, we could say, differential operator. Delta is the dimension of the primary field phi delta, and P and zeta, which appear here, are doubly periodic analogs of the functions 1 over z and 1 over z squared, so that they have the corresponding poles at 0. So 1 over z and 1 over z squared would be what appears in the ordered identities on the sphere. So we basically just replace them by some doubly periodic analogs, at least in the singular part. We also should add some regular part here, in particular, derivative over the modular parameter. It's quite natural that it appears in here because, well, the change of the conformal, a change of parameter tau could also be thought of as some change of the metric, which the stress energy tensor generates. So yeah, that's basically the most important term in this equation. And the eta 1, which appears here, is a constant in terms of dependence on z and x. it depends on the tau and is given by the following series. So another common feature which all the CFTs that we consider have is the modular properties of one-point functions of primary fields and also of Virasoro descendants. It basically states that these averages, well, due to translation invariance, they do not depend on the point of insertion of phi delta. However, they transform not trivially when we perform modular transformations. In fact, they are modular forms of weight delta. So they invariant under the shift tau to tau plus 1. And if we change tau to -1 over tau, they transform as follows. Yes, so now let's move on to properties of more specific properties that for CFTs that we consider. First, the ghost CFT. Well, this is basically just a free CFT with the action d bar c plus c plus b bar d c bar. BC are Grassmann valued fields. In our particular case, they are of dimension to -1. And it's not really important to what we'll discuss now. So the somewhat peculiar circumstance about how we should treat this system in this context is the boundary conditions. So basically, as I mentioned before, the ghosts come from gauge fixing or Faddeev-Popov determinant of the operator, so basically D and D bar. So the B and C fields should be quantized with the same boundary conditions as fields in the other sector, the Liouville field and the minimal model, which are periodic in both directions on the torus. It means two facts. First, that they decompose in integer Fourier modes in terms of the coordinate z. And also that we need to understand the correlator in the ghost sector as a trace with insertion of parity operator that counts the fermion number. If we would have an antiperiodic boundary conditions, then the function one integral, the corresponding function integral would calculate just the trace of the Gilbert space. So yeah, so these are the algebra of modes, Bn and Ck. They anti-commute almost always, except when L plus K equals to 0. All the other anti-commutators are also 0. From what I discussed here, it follows that the partition function, in particular, average of unit operator in the ghost sector, is equal to 0. The simplest correlator which is non-zero is the following two-point function via z CRW and the corresponding anti-holomorphic fields also inserted. It could more or less easily be computed from what I described before, and the formula is as follows.
Excuse me, but B times C must has a pole. Where? How could it disappear?
Basically, what you're saying is that B and C have the following operator product expansion, right?
Yes, right.
So this is precisely why this pole disappears, because the average of unit operator is 0, as I said here. Yeah, so
I see.
For higher correlators, for example, with like BC, we would obviously see these poles when we compute the corresponding correlators, but this particular one, we don't have dependence of Z and W at all. It only depends on Q. This is a very important property that we'll also use in what follows frequently. It can be understood as follows. Basically, the simplest correlator is saturated by the zero modes of fields B and C. So we can substitute B0 here and C0 here. And when we do this, we calculate this. We can calculate this answer. And yeah, so the zero modes of B and C are on torus just constant functions of Z and W. So no dependence on these coordinates is to be expected. All right, so now let's discuss quickly the correlators in two sectors, minimal model and Liouville theory. So as I said before, schematically the form of all these correlators is just the trace of the Hilbert space, which is the basis in the Hilbert space is parameterized by conformal dimensions delta, which are in the spectrum of the theory, and two Young diagrams, lambda and lambda bar, which label various order descendants of the corresponding primary fields. For the case of 2 to the p plus 1 minimal model, the fields in the spectrum are the general fields phi 1m with m from 1 to p, as written here. And the series in lambda and lambda bar actually can be summed up to a certain special function called conformal block. It's basically because it only depends on conformal dimensions and Q, because the ratio of these matrix elements is completely fixed by conformal symmetry. And this matrix element, diagonal matrix element, which you have here, is basically a structure constant, which appears there. And here I just wrote the expression above using the parameterization for central charge of the minimal model as follows. The parameter B will be defined shortly, but it's, for our case, it's square root of 2 over 2p plus 1. All right. So the similar formula is valid in Liouville theory, but in this case, the spectrum of the theory is continuous, and the terms in the sum are parameterized by one real parameter p. Yes, the primary fields in the spectrum have dimensions p squared over 4 plus p squared. Is delta of p. The central charge of Liouville theory is in the same notation 1 plus 6 q squared q equals v plus minus 1. And here I use the following parameterization of conformal dimensions. Delta of A is delta of A is A times Q minus A. So the fields with this conformal dimension have this parameter A, or equivalently the one with negative P. And well, the structure constant which appears here is given by the OZZ formula. It contains so-called epsilon functions, which relate to Barnes double gamma functions. We won't need much of its properties in this talk, other than the position of its zeros, which are equivalently the poles of the structure constants. So there are 4 series of poles, which are described here with M and N non-negative. Yes, so the final thing to say is about the integration contour gamma. Well, is this integration contour is just a real line if A itself lies in the spectrum, or more generally for when this inequality is satisfied. But if we take A outside of this domain, and then we should, from the requirement of analyticity, either deform the integration contour or add some discrete contributions, which are referred to as discrete terms, to this formula. And discrete terms are the residues of the poles which cross the real line, the integration contour in the basic domain, under analytic continuation in A from this domain. For example, if A equals A1n, corresponds to degenerate Liouville field, this condition is not satisfied because A is either less than 0 or greater than Q. So we have discrete contributions, which are basically the only thing that contributes to a correlator in this case, because for this A, the structure constants actually becomes 0 because of this factor. Right. So now let me shortly repeat myself about what the minimal real gravity is. Basically, it's CFT consists of 3 parts: the minimal model, Liouville theory, and ghosts. Ghost CFT has a central charge of -26, and total central charge should be 0. So C minimal model plus C Liouville should be equal to 26. From this condition, we actually learned that the parameter B, which appeared in discussion of Liouville correlators here, is the same B as I defined previously for the minimal model, square root of 2 over 2p plus 1. If these parameters are the same, then the total central charge is equal to 26. This condition ensures the nilpotency of the following charge, which generates Grassmann odd symmetry called density symmetry. And well, in kind of string theoretic fashion, we will be interested in the cohomologies of this charge. We said it is nilpotent, so Q squared equals to 0. we can define the homologies of this operator. A question?
Excuse me. Let us return to that formula. I think it's wrong because it's zero about B and C. The non-zero formula is for C only, without B's. This formula is wrong. It is equal to just zero.
No, it's not. It cannot
surely,
be
surely because
okay.
It's zero ghost number. The correct formula is the average of C bar C is not zero.
No. I'm sorry. On the torus, what you're saying cannot be right, because on the torus, the ghost number anomaly reads that NB minus NC should be 0. In general case, it's 3G minus 3.
Excuse me, but on torus, you take zero ghost number. It's all correlation functions in zero ghost number are zero. It must be 1.
No, it's not. Well, the requirement for the correlation function to be non-zero is as I wrote. For a general Riemann surface, it's the right-hand side is 3G minus 3. For example, on the sphere, we should have 3 C fields. And we have G equals 1. So we should have equal number of B's and C's.
It's strange.
I'm not sure where the one you are talking about comes from, but it's, well, you can just calculate this correlator in the Hamiltonian language using what I told here, and make sure that it is equal to eta of q to the power of 4, which is non-zero.
Yes, it is right, of course. Anomaly of ghost current is equal, proportional with this expression.
Well, yeah. So if there's no more confusion, let me proceed. Sorry. Right. So what I was talking about, the homology classes that we will be interested in are the so-called tachyons, which are built from primary fields of minimal model and Liouville theory. They are first are combined in this way. With the requirement that the parameter of the Liouville field solve this dimensional constraint. So total dimension of U is 1, 1. This operator U is plus a density that could be integrated over our surface, through in our example. And if we calculate the Biarritz variation of this expression, it reduces to integral over of the derivative. So up to solidity with boundary terms, which can obviously appear, it is 0. we can also additionally address these UMN fields with the ghost C1 of dimension -1. So this T has total dimension 0, the primary field of total dimension 0, and it is just VRST closed. So these are equivalent, in some sense, representations of the same homology class. We will not be using this option. It is not relevant for the one-point correlators that we consider. So we will not be integrating over our surface. And TMN is just a local operator that can be inserted on some point on the torus. Another important set of cohomology classes, which are specific to minimal gravity in a sense, are ground ring operators. They are built from Virasoro descendants of the product of degenerate Liouville fields in minimal model and Liouville theory on the same level Mn. So we built this operator, Mn. It has dimension 1 minus Mn. And then we act by some polynomial of Virasoro modes and ghosts of total degree Mn minus 1. So again, the dimension of all Mn is 0. One can find HMN such that this operator O is BRST invariant up to the terms that contain singular descendants of degenerate fields, which are, well, the highest vector of the submodule in the corresponding Virasoro Verma module, and which we usually put to 0 when constructing the CFTs, both minimal model and Liouville theory. So this is just like what we would get if we proceeded with a straightforward algebra, and modulo these singular descendants, it is 0. And the statement is that we can find HMN such that this condition is valid for any M and N. No general form of H is known, but case by case, by demanding the requirement above, it can always be found. The two particular cases, just to give you some understanding of what they might look like, is H12 and H14. If I wrote the Gauss part here, it probably would be very, very bulky. So, and also it's not important in our particular setting. So, well, the general structure, at least for the operators H1n, which are only relevant to our case, to P+1 model, is the sum of the form P of Lm times C times pk form times C times D to the kb, from k equals 0 to n minus 2. Sorry, minus 1, I guess. And here we have, okay, sum goes from 1 to n minus 1, and there's also P0 of Lm. Okay, n minus 2 here. Sorry. No. Sorry, I'm confused. From 0 to n minus 2. Yes, that's right. Here we have p minus 1 without ghost nodes. Right. So let me now discuss the most important ingredient for derivation, which are the higher equations of motion of Alexei Zamolodchikov. These are a set of operator relations in Liouville conformal field theory, which concern the so-called logarithmic operators. They are of the form Liouville field phi times a primary times a Liouville primary VA, where A parameterizes the conformal dimension as before. Equivalently, we can think of them as the derivative of primary fields over this parameter. Well, obviously, these operators are in a sense bad and unusual. They a kind of a formal construct. Introduction of them is somewhat of a formal construction from the point of view of from the usual point of view of conformal field theory. But well, the simplest example of such a field is the Liouville field itself, which corresponds to A equals to 0, or another notation that I described here. It's V prime 1, 1. So V prime m, n is the logarithmic operator related at the degenerate dimension. As we know, Liouville field is subject to ordinary Liouville equations of motion, which look as follows. And it turns out that it can be generalized to general m and n in the following way. So we act on V prime with operators, which would create a singular descendant level of mn if we had Vmn here without a prime. And the result can be equivalently written up to contact terms. So this is the equality which is varied under a sign of a correlator up to contact terms. And the constant Bmn is explicitly known. It's written in here. So why is it useful in our context? Well, basically because Vm minus n is the dressing, other dressing operators for primaries of minimal model. So I remind you that we had, so it's written here. Umn is this field of dimension 1, 1 is given by dressing of this primary with such a Liouville primary. Yes, so we can, using the higher equations of motion, then write this density as follows, where the definition of theta prime mn is introduced here, and the right-hand side can be further written using this property. This is basically more or less straightforward algebra. So it is quite easy to understand this equation. Say if we did not have a prime here, what we would get? DHMN minus Q. Well, the equivalent, I mean, this formula is a bit more complicated than what I'm trying to write right now. So this is the analog of this formula for non-logarithmic operators, which again, this is a combination of singular descendants, so it is basically put to 0. We can rewrite Q or D right here as the intercommutator of VRST charge and the ghost mode B-1. So yeah, so it's Q B-1 minus plus B-1 Q. And then this equality is becomes obvious, because when we act this operator on HMN ZMN, first we act with BRST charge, and according to what I discussed previously, we have C DMN theta-MN. And then B-1 acts on C and gets just 1. So this is the holomorphic analog of this relation. But introduction of the prime somehow complicates things a little bit, but not much. If we act with both homomorphic and anti-homomorphic operators of this form, we can reduce it to what's written here. So the result is that up to VRST exact terms, integrated density UMN can be replaced with the derivative dt bar of logarithmic partner of ground ring operator O. I'm sorry. So there is another form of these higher equations of motion. It was first found in the context of super gravity, but also is also valid in the bosonic case. So if we additionally address density with the C ghosts as before, it could be currently written as an action of VRST charge on O prime. One can very easily, again using straightforward algebra, derive this this equation from this one. I mean, well, the consequence of equation 22 of 21 from 23. It can be easily done. Right. So now let's discuss what we will finally be calculating. What are the 1-point numbers? It's not precisely something like the average of TMN, because this is equal to 0, as we discussed, because of the Gauss number anomaly. You need to have an equal amount of B and C fields. But we can address the TMN additionally with B ghosts, and then integrate over the modular space of unstructured tores. Due to the properties we described before, this correlator is a modular form of weight 2,2. So this integral is a well-defined correlation number in the sense that it doesn't depend on the choice of the fundamental domain, which is the modular space of unstructured tores. So now I will proceed to discussing the principal steps of the calculation for the case n equals 2, the simplest one. Comment a little bit on more difficult case 1, 4, and some more general cases. But n equals 4 will be probably without technical details. because I'm already speaking from almost an hour. So what are the steps of the calculation? First, we use the independence of this correlator on the positions of B and C ghosts, and move the, well, it's just to be well, yeah, so we move the B ghosts to some, here it is assumed that they are all inserted in the same point, but actually that doesn't, it doesn't really matter. We can move B to some other point Z, and then we have a composite operator CC bar V, which is the tachyon. We rewrite this tachyon operator using higher quantities of motion in this form. And then we, yeah, so as written here, without the numeric factor Bmn to the -1. And then we can use the distributive character of BRST charge to write it as Q exact terms plus Q bar exact terms plus this term where Q and Q bar act on B and B bar, which gives a stress energy tensor of the full theory. So yeah, this Liouville plus method plus ghosts. Oh, well, why do we ignore the BRST exact terms? Well, the formal argument is as follows. So if we look at this correlator again in the Hamiltonian language, so as a super trace of the total Hilbert space, it formally evaluates to 0 if we use the two facts. First one is that Q anti-commutes with the parity operator. It is, well, Grassmann odd, and it commutes with Virasor modes, in particular with L0. So then we can just like move Q using the cyclic property of the trace to the other side, and we have that trace of this anti-commutator becomes 0. This argument is a bit shaky in our case for the reasons that we have these logarithmic operators here. They are not precisely they do not precisely lie, or the corresponding states not precisely lie in the Hilbert space of MLG, and well, correspondingly their action is only defined on some extension of the Hilbert space. But we still would like to discard the total Q exact terms to move on, and well, at least knowing that in the end result we would find what we would expect from matrix model approach, it gives some justification to this procedure in this case as well. So right, we have this correlator where prime stands for derivative over the parameter of the Liouville field A. If we move, if we take this derivative out of the integral over tau, we are left with this correlator, in which, in this particular case, a lot of the terms actually do not contribute, because, well, again, the ghost zero modes are not saturated. So, for example, if you take this term in the first bracket, so there is the average QZ above Z bar -1, -1. Move something here. If we want to, when we evaluate the ghost part of this correlator, it only comes here from T ghosts of Z. T goes to Z, there are two terms that look something like that: B dc and C dB, normal ordered. But these correlators actually both vanish because the correlator BC is independent on the positions of the fields. So yeah, if we differentiate it over W, as we have here, we get 0. Similarly with this one. So the only thing that contributes is term where we ignore these operators. BC, V bar, C bar, V if you want. In this particular case of T12, we can now immediately use word identities to get rid of stress tensor insertions, because we have a primary field in the correlator here. Just a quick reminder of how the word identities look. And from this formula, we will also discard the second term, which contains derivative over x, because we are dealing with one-point functions, and they are supposed to be translation invariant. I'll give a few more comments on that in the end of the talk. So we have this bracket and the corresponding one from anti-homomorphic insertion. Now we differentiate over A. Since the total dimension of the field BCVA phi12 is 0 when A equals A12, if we don't differentiate the prefactors coming from word identities over A, which contain the dimension delta P of Z equals to eta 1. So if we don't differentiate this conformal dimension, we are left with this thing. So we differentiate again the V here. If we do differentiate these prefactors, we obtain this contribution. One alarming sign is that it still has the Z dependence that are points of insertion of energy momentum tensor, stress energy tensor. Here it's the bar, here it's the. Although we knew that in the starting expression there was no dependence on the bar. We will comment on that very shortly. But we still are glad to obtain this result, because all contributions that are left are expressed in terms of derivatives over tau or tau bar in the moduli space. That means that the integral over f can be reduced to boundary contributions for both cases. So one can choose the fundamental domain different ways. One standard one is the shaded domain in here, the region of 0. I didn't write it here, but all right. So some boundary components are actually glued, identified, because one can, for example, come from this point to this point with the boundary transformation tau to tau plus 1, and also from this one to this using tau to minus 1 over tau. So what we would think of as a boundary with this moduli space is only the well, it's only what happens at infinity over tau here, where q tends to 0. It is good because in this limit, q tending to 0, most of the terms that appear in the correlators we consider die out because they're proportional to positive powers of q. So we expect that this boundary contribution, this for this boundary, can be calculated exactly by computing only a finite number of contributions to the correlator, which are of order q to the 0. Right, but let's first address a problem that was announced before, but that in this contribution we have explicit dependence of over z and z bar. Well, actually, the solution is that this contribution is 0 because this average is independent of both tau and tau bar. It is non-zero, but independent of modular parameters. It can be easily proven algebraically with the following change of relations. Consider the derivative over tau of this correlator. Using word identities in the other way, so to speak, from right to left, you can write as an assertion of the energy momentum tensor. Then you can replace this correlator with a full form of O12, adding the terms with L minus 1, minus M minus 1, and so on. And then use that the energy momentum, use that the total energy momentum tensor is BRST exact. It's the action of BRST charge on B. And it's written as a total Q exact term minus the one where Q acts on O12, which is BRST closed. So in total we have that this derivative over tau is 0. It's basically what we did before, but in the other directions and without the primes here, which is why it's simpler. So this is one way to illustrate this, which might be not really intuitive if we start with straightforward expressions for the correlators, which we obtained earlier. In what follows, we will still calculate that, but the statement that this correlator does not depend on tau or q basically means that there is a certain identity concerning toric conformal blocks with degenerate dimension. Well, maybe it can be understood independently. I don't really know if there is a way to check this analytically, not order by order, but well, at least I know what is expansion of FL of the family as a series in Q, and knowing this, you can just check that this equation is valid. So for the general case of O1K, this method is generalized straightforwardly, but identities like this should become more non-trivial, mostly because they probably don't factorize into a holomorphic and anti-holomorphic part. So it would be some expression some expression of this form. sum with some coefficients for some intermediate dimensions, delta P, delta M, Pm equals to constant, and something like this.
But it's constant in both tau and tau bar, right?
Sorry, what?
I
Yes,
mean,
right. Mhm.
so I mean, kind of formally, you can think of like sending tau bar to infinity, for example, or to zero, whatever. And in a sense, you will decouple you'll take on leading asymptotic in tau bar.
Mhm.
So I mean, it still predicts some holomorphic identity, I guess, no?
Well, perhaps.
So
No, yes, maybe you're right, but
this
it's-
this bilinear combination is a constant of both tau bar, right? That's what you're saying.
yes, yes.
Mm-hmm.
Well, these coefficients also depend on tau and tau bar.
But that's universal. I mean, universal by
Right.
some degree, something like
Mhm.
that. Mm-hmm.
Sorry, may I ask a question?
Yes,
Yeah.
sure.
But you have an expression for FL and FM, or is just general?
Excuse me once again. I didn't
Do you, I'm confused. Do you have an expression for FL and FM, or 29 is some kind of general expression formula?
Right. Yes. For FL and FM, I have, for example, a series, a representation as a series in Q.
Sorry,
Using
where do you have the expression of F?
No, Juan, these are universal functions. They just defined, I don't know, by conformal symmetry. They're just known. Basically, yeah.
And the question is, so we can find FL and FM, I mean the block from this expression, right? Or we need something else?
well, from this equation, no,
Yes.
we can, from equation 29, we cannot find that.
Okay.
Well, first of all, FL is defined for general parameters, intermediate dimension. Well, and this one, and here we have very specific parameters here, and here, and well, yeah. So if you want a general expression for a conformal block, you should use some other methods.
Okay. Thank you.
All right. So, by the way, Alexey Viktorovich, how much time do I have?
It's up to you. And
All right.
half an hour, that fits and everything.
All right. So then I won't hurry much. Right. So another issue that can be, well, that should be considered in this derivation is basically that we can sort of glue together these boundary lines here and here when reducing the integral over the fundamental domain to integral the boundary, only if the integrand is modular invariant, which is not the case here. Since we have a logarithmic operator in the average, this correlator is actually not modular invariant or even covariant. Let's understand how it transforms under modular transformations. So we know that the one-point functions of primaries are modular forms, and if the dimension is equal to 0, the correlators are modular invariant. If we take this primary field with A with arbitrary A in the vicinity of A12 and substitute it in this equation 4, and differentiate it over A at a point where the dimension is equal to 0, we have this equation. So this is what we would get for the average of primary fields. It is covariant, or rather invariant. You can just change tau to -1 over tau. And here is the additional non-homogeneous term, which has logarithm of tau tau bar, and the delta. Did I define? Right. Just as a reminder, of delta is the average. Oh, the delta of tau is the average of phi delta. The modular parameter tau. So basically, for the ground ring operators, here we have an average of O prime, is written here, and here we have an average of O12, which, as you know, actually does not depend on tau at all, which we'll use in what follows. Right, so in terms of real coordinates r and phi, with tau defined as written here, we can rewrite this equation like this, and then we can differentiate it with respect to radius and set r equals 1. Why do we do this? It will be apparent shortly. So we have the sum of these two derivatives at the point phi and minus phi on the unit circle. Here's the unit circle. Here's the point phi, and here's the point minus phi. The sum of derivatives over r of this average of O prime is equal to this term, tau independent term. So we finally do what we were planning to, and rewrite the expression that we had, integral to tau is squared over d tau bar average of O prime using the Gauss theorem, right here. And we have contribution from the boundary at infinity, which is given as follows. And also, we might get a contribution from this part of the boundary at finite tau, basically at model tau equals 1. We don't have contribution over the vertical parts with real part of tau equals plus or minus 1/2, because the correlator of O prime is invariant under translations tau to tau plus 1. Yeah, so the corresponding boundary contributions do cancel. As for these arcs, it can be written in this way, which reminds us of the equation we obtained previously. And we see that it is actually non-zero and equals to this integral. So it is not zero, but it's easily calculable because the average of O is independent of tau or phi, so we can just move it out of the integral and take it to yield pi over 6. So all the boundary integral over this arc reduces to this additional term. This is basically the answer in terms of boundary contributions which we obtain for our tachyon average. And well, as to this point, all the steps could be directly generalized from O12 to other cases. For example, from O14 we checked in the paper. So what's left is to calculate these averages, average of O and the average of O prime. Since this average is independent of tau, we can also calculate it in this limit out to E infinity, which will be convenient because of the reasons that we discussed. So let's first calculate that. So first we have the average in the minimal model. This is the formula that was already written before. The simplification for this particular case is that only one term actually contributes to the sum, because this diagonal structure constants is almost always zero. It's only non-zero if we are at m equals p. Why is that? Well, basically, we have the operator product expansion like that: phi1 k plus 1 plus phi1 k minus 1. In general case, there's no diagonal channels, but m equals p sits at the boundary of the Katz table for the minimal model, and there is an identification k phi1k is equivalent to phi1 to pi to p plus 1 minus k. In particular, phi1p and phi1p plus 1 are identified. So in this sense, there is a diagonal channel here, because phi1p is the same as phi1p plus 1. Structure constant in this particular case, well, just for illustrative purposes, it's given here. Again, the relevant formulas for Ghost and Liouville correlators are here. We can basically multiply these expressions for all three sectors and simplify it further. So if we have a certain integral over p of the some functions which can be expanded in series in Q, and the leading term, if we just calculate that, depends on p in the following way. If p is real, even this leading term tends to 0 on the boundary of moduli space, so the contribution from the continuous part of this Liouville expression vanishes at Q tending to 0. So it also vanishes for another reason when A tends to the giant values A1 to, as I said before, the structure constant tends to 0 in this limit. There are, however, not only continuous, but these discrete contributions that we were talking about before, which come from the poles of the structure constants with imaginary p that cross the integration contour when we analytically continue A to be close to A12. The poles that contribute are the ones for which two epsilon functions in the denominator of structure constants become zero in the limit. There are two such poles at the following values of P. And when A tends to A12, it becomes is written here. If we substitute this imaginary P in this formula, we see that contributions from these discrete terms are of order Q to the 0 already. So, well, we first of all don't need to worry about conformal blocks. We only leave the leading contribution from both FL and FM, which are normalized in a way that they start with 1. It's similar with 1. And also, the contributions from these poles are equal because they are connected. This refraction P2 minus P, which is actually basically the corresponding primaries in the Liouville theory, have the same dimensions and are identified up to some constant, and this constant is but one can show that it basically constants in this sort of calculation. So I mean the diffraction coefficient is introduced in such a way that the contributions from two poles are actually in this correlator are actually equal to each other. All right. So summarizing all that, we have a very simple expression for the average of O12 at tau2 to infinity and for any tau correspondingly. It is a product of minimal model structure constants times the residue of the Liouville structure constant at the degenerate point, and some numerical coefficient. Well, yes, yeah, that's it. And well, I forgot to say that from Gauss correlator, we also only need the leading contribution. So instead of at of Q to the 4, we only need Q to the 1/6. All the others is some kind of product, y minus Q to the n. Yeah, we only need this one, this term. So what would change if we consider the logarithmic field of prime 1, 2? This contribution. For the average of O prime 1, 2, we need only to keep the terms which are proportional to tau 2, which is the measured part of tau, because we differentiate over it. Well, the average of O prime obviously depends on tau, at least because of how it transforms under model transformations. But there's a leading term which is linear in tau 2, and all the others tend to 0 in boundary model space. At least the derivative tends to 0. So how would we get this contribution proportional to tau 2? To get this, we need to differentiate over A, the prefactor of this form, when we still haven't put A equals A12. If we differentiate it with respect to A, tau 2, since this is actually the same as written here, there is a this little typo here. Well, I mean, it should be an additional exponent that cancels this sort of divergence when a equals a12. Right, so it won't blow up in the boundary of modular space. So if we differentiate it over tau and over dA, we have basically the same as the average for O12, but with an additional factor. Now we can sum the two terms in this formula together, and we have the following answer for a tachyon 1-point function. Just a few comments on the case of H14. As you have seen in the expression before, relevant for this calculation part of the operator H1n contains not only ghosts but Virasoro modes as well. So we have in the minimal model Liouville part the correlators of non-primary fields. We cannot, for example, immediately use the word identities. Well, we can, but we first should use the ones for the double tensor insertion, for example. Still, as I said before, everything that leads up to the expression in form like that is straightforward algebra and goes along the same lines. Both the statements that ground ring average is independent of tau and tau bar, and that the tachyon correlator reduces to total derivative of this form are valid. Both these claims are valid. So something a bit more interesting appears when we calculate these ground ring averages that appear here, average of O and O prime. Both for minimal model and Liouville correlators, 1-point functions in both of these sectors. There are now two contributions, which are written here. Contribution from two intermediate channels, which are numerated by number m for minimal model and by Liouville momentum p in Liouville theory, respectively. And when we multiply the two expressions, we have basically 4 different terms, some of which are not of the leading order q to the 0. Moreover, one of them is actually of contains negative powers of q, which should be alarming because it means that it blows up on the boundary of modular space. Well, actually, it doesn't happen precisely because of the additional Virasoro modes in H14. Let me just remind you how it looked like. Yeah, so the relevant part for 1-2 is here. We have an additional Virasoro mode, combination of Virasoro modes O -2 minus M -2. In leading terms, these Virasoro modes contribute a certain numeric factor dependent on the intermediate channels in minimal model and Liouville. And this additional numeric factor is dependent on P and M in such a way that the two so-called wrong terms, which are not of the order q to the 0, cancel. And the two remaining terms is let's say m equals p and p equals to this thing, or m equals p minus 1 and p equals to this. turn out to be equal because of the, well, it just can be explicitly calculated using the forms of structure constants in this case. So we have each channel in terms of minimal model, or each reflection-related pair of Liouville discrete terms give half of this counting average. When we consider the logarithmic operator, these two pairs are respectively additionally multiplied by Liouville momenta up to a factor. And this derivative is expressed in terms of the average of 014 in this way. Again, we can combine these two expressions to get the tachyon average. And now we extrapolate these results to a more general case. Extrapolation is done for O1k with even k, or O1 to k as written here. So just like extrapolating our observations, we can assume that in a particular normalization, which is, well, it's not really arbitrary, it's very much can be computed what kind of normalization I'm talking about. The average of O just counts the number of channels, more or less, channels that contribute to this average. The average of O prime is different from the average of O by, again, multiplication of this number of channels up to some factor. Again, this is just an extrapolations of the formulas like this and like this. Right, and then we have the conjecture generalized answer for a tachyon average in this form, which in this normalization reduces to a very simple symmetric with respect to reflection, with respect to symmetry of the Katz table expression. And this polynomial is precisely the result of, in the matrix model approach for the one-point correlator, as obtained by Belavin and Tarnopolsky like 10 years ago, I guess. All right. Well, I'll finish just with a few more comments. Some of you might be interested in the question, why do we only consider the tachyons with even k? Well, some interesting problem that might be interesting to resolve is that from the case of odd k, the arguments above do not directly generalize. The simplest demonstration is what appears to be the simplest correlator, which is the Dressed unit operator. In this case, the ground ring operator O11 is just product of unit operators in Liouville minimal model sector. So the polynomial H is just equal to 1. It doesn't contain ghosts or Virasoro modes. If we use higher equations of motion and commute the velocity charge with the B field as before, we reduce the tachyon average to the following correlator, which on one hand vanishes because zero modes are not saturated in the ghost sector. It is a contradiction because the tachyon average we started with was actually, well, it's one of the few results that was computed long before us. In genus 1, it was computed analytically by Beshatsky and Klebanov a long time ago, and well, it is known to be non-zero. A partial answer to the resolution of this problem is that although the ghost part of the correlator is zero, the Liouville part is in fact infinite. Actually, even the partition function on the torus of Liouville theory is infinite because of, well, it diverges because the spectrum is continuous. And the average of logarithmic operator is even more divergent. Well, the speculation is that zero and this infinity should cancel somehow, but we did not yet, haven't yet understood how exactly this happens. Speculation is motivated by comparison with the following issue. Logarithmic operators, even in ordinary Liouville theory, appear in some sense to violate the property of translational invariance. For example, it can be seen for ordinary Liouville equations of motion. This is how they look. The average of right-hand side can be calculated exactly. It is non-zero, but the average on the left-hand side is a derivative of some y-point function with respect to coordinates on a torus. And, well, in this case, the resolution is exactly in this constellation between this naive zero from translational invariance and the singularity of the diagonal structure constant. In paper in appendix, we described how this statement can be made precise. The situation in Liouville gravity is a bit different, but reminiscent of this calculation. So despite all that, we still can say that our method in some sense is applicable to tachyons with odd k, because well, in MLG there is a reflection relation which interchanges even and odd t's. This is just basically an inequality up to some normalization factor. But the procedure itself that we used for the calculation would be different for these two cases, because there is no there's no similar reflection relations for ground link operators. So this is not true. Right. So if we use this reflection relation before, applying our method, we could still obtain some answer for this average, and the expression that we obtained right here would obviously be consistent. It respects this reflection symmetry. Right, so I think that's what I would like to finish on. That's basically what the main points the paper we described. Well, there are some directions in which one can generalize this, try and generalize this. The obvious ones are for general PQ minimal model series, not only Li-Yang, or maybe somewhat more interesting one could study two-point functions on the torus, or where some, well, most probably conceptually new problems arise, similar as when we transition from say 4-point function sphere to 5-point function sphere. And no, yes, I guess that's it. Thank you for your attention.
Thank you. So, colleagues, please, your questions. Somebody is still alive.
Yeah,
So
I'm sorry.
To say that you are right, I completely forgot about this point on torus with B and C.
All right.
So, concerning these identities between the conformal blocks,
Right.
does it imply that, I mean, they have poles in the intermediate dimension? Does it imply somehow that the addressing block has zeros at all those points?
Sorry, once again,
I mean,
we have very particular intermediate dimensions in here.
this is
Well, it's not for general intermediate dimension. Well, moreover, these two are connected in a very simple way. This one is actually addressing. This field actually is what addresses this one. Yes. So the sum of these two dimensions is equal to 1.
And such type of relation appears only for torus block, but not for sphere. Or we somehow just haven't found it for the sphere.
Well, perhaps. I mean, there's not. Well, how would I guess one could try and find some relations like this. Say, well, right. Consider like a 3-point function, tachyon 3-point function. W with insertion of the ground ring operator. So this can, first of all, it doesn't depend on Z. And second of all, it can be easily calculated. One can use the operator product expansion of obvious W. Oh, sorry, I'm using enough notation in the stock. It's T here. T1, K1, T1, K2, T1, K3. So this basically can be calculated, and it is independent of Z. On the other hand, it has some expression in terms of conformal block. But, well, I think it won't be that.
So, but these conformal blocks will be like a minimal model. That would be the degenerate block, but in Liouville, it's addressing, right? Sorry, I just.
Well, O1N also contains. So one of the fields is also degenerate in Liouville, right?
Yes. O1N, yes.
Right. So I haven't really looked at it. Maybe it would reduce to something beautiful, but well, it's not obvious. At least even for O12, probably the analog of this sort of relation would be more complicated because
it's not important here that T's are degenerate. I mean, they can be arbitrary, and this also holds, right?
Yes, right.
Mhm, mhm. Mhm,
Independence of that, for example, also holds, of course.
mhm. Interesting.
Maybe it's worth looking into, but
Mhm,
I don't know.
mhm. Okay, other questions? If somebody has, please go ahead. Mm.